Welcome to the Ontario High School video podcast that deals with how to represent the role of energy in physical changes through the use of energy bar charts. This PowerPoint that is the basis for this was not prepared by me personally, but I will give credit to the Arizona State University Modeling Chemistry Project for this. So thanks to ASU, and stay tuned. Let's take a look at how we construct an energy bar chart. We'll use the example of a cup of hot coffee that's cooling as it sits on a table. So we want to determine what's in the system, and then everything else will make up what we call the surroundings. And the system is very simply what we want to study. Everything outside what we want to study is the surroundings. And so you can see that we have an initial and a final grid, and then three types of representations of energy here. ETH, which represents thermal or heat energy, better actually described as the kinetic energy of the particles. EPH, which is the energy of the interaction between the particles, or also known as the phase. And then E sub CH is chemical potential energy, and how we represent these is what we're going to go after here a bit. Now, the coffee cup in that round circle is what we say is the system, and that's what we're studying. So this is just the base of what we're going to work from. Whenever we represent the role of energy in a physical change with energy bar charts, we'll need to make a decision as to whether the E sub CH, the energy of the chemical potential energy, is involved. So we're starting with a cup of coffee. The coffee does not change. It's still coffee at the end of the time that we're studying. And since the particles are not rearranged to form new substances, we're going to be able to ignore E sub CH for this particular system. We want to assign values to the energy of interaction or the energy of the phase. And because of the interaction between particles, the energy stored due to the arrangement of the particles is ranked. The energy of interaction in solids is less than that of liquids, which is less than that of gases. And you'll be able to link that back to our earlier discussions about kinetic molecular theory. We're going to choose to arbitrarily represent these phases by always representing solids as 1 bar, liquids as 2 bars, and gases as 4 bars. And this is a rigid system that must be adhered to. Okay? When you see a solid, 1 bar, liquid 2 bars, gases 4 bars. In this case, we're dealing with coffee, which is a liquid as we study it. So the energy of interaction or the energy of the phase, we're going to put 2 bars for its initial energy and 2 bars for its final energy. Next, we need to represent the energy of the kinetic energy, which is represented by ETH or thermal. The bars depend here on temperature. So because we're looking at hot coffee that is going to cool to room temperature, we're going to assign 4 bars for the hot coffee initial, and then at room temperature we'll assign it 2 bars. You could make this 3 and 2 or 3 and 1. Other values can work, but we always want to be consistent in our representations. And you'll see as we work this out further why it's important, this consistency. Well, if we had a total of 6 bars of energy to start, and that's in our initial system 4 for the energy of the temperature related to temperature, energy kinetic, or E sub TH as we represent it here, and then 2 bars for the energy of the phase or the interaction energy. In our final system, we have 2 bars for the energy of related to temperature, E sub TH, and then we remain a liquid, so it's 2 bars for the energy of the phase. There's a difference of 2 bars between those. There are 6 bars on the initial side. There are 4 bars on the right-hand side. So energy had to leave the system in order for this to be true. And we're going to represent that energy by showing the 2 bars with an arrow labeled Q because it's heat energy leaving the coffee cup system. And so that's what we've done here. So we've accounted for our initial energy state, our final energy state, and where the energy went. And it went from the system to the surroundings. We're going to look at a system that has a phase change. We have a tray of ice cubes at -8 degrees Celsius placed on a counter and becomes water at room temperature. And here's what we know. The system is a tray of ice cubes. The solid water turns to liquid water, so there's no change in the identity of the particles. It's still water, so no chemical change has occurred. The interaction energy or phase energy increases. It's going from a solid to a liquid. And also the temperature increases, so the thermal energy or kinetic energy increases as well. And we're going to go ahead and represent these changes in a bar graph. Why don't you go ahead and stop the podcast and do that, and then come back and check and see how you did. Here we have a look at our initial and final states. We're going to start our temperature at less than a bar, the energy associated with our temperature. So we're going to use half a bar of energy there. And then the energy of the phase, because it's a solid to begin with, has to be 1 full bar of energy. Now, it changes temperature to room temperature. And since we represented room temperature with 2 bars before, we'll just do that for consistency's sake here. And our phase energy, because we're going from a solid to a liquid, will increase from 1 bar to 2 bars. So that's what we've shown so far. What we haven't done is shown energy flow, but that will show up on the next slide. Since the energy of our system after the ice melts is greater than the energy of the system before the ice melted, that energy had to come from somewhere. So the energy in this case flows from the surroundings to the system, and so you will draw the number of bars that were added, in this case 2.5 bars of energy. So you started with 1.5 bars, you added 2.5 bars, and we ended up with 4 bars of energy represented in the final system. So we draw the 2.5 bars, we label that Q for heat energy flowing from the surroundings to the system, and we put an arrow on it to show that it is flowing into the system from the surroundings. And that's how we account for the energy. So very simplistic explanation of energy bar charts, and I hope you do well with this. We're at the end of this video podcast. I want to leave you with a quote from one of my wife's favorite authors: "Some things have to be believed to be seen."